The purpose of this video is to demonstrate the operation of a bipolar transistor semiconductor device. A transistor has 3 pins: base, emitter, collector. It can be operated in 2 modes, either as a signal amplifier or as a digital switch. The circuit that has been wired up in front of us has been wired up using electronic kits, and it is operating as a common emitter amplifier. So what do we mean by amplifier? What we mean is we're taking an input signal and we're increasing the amplitude. So the example would be if you have a mobile phone that's receiving a radio signal through the air, its amplitude will be varying depending on where you are geographically. Inside the mobile phone, the signal needs to be a certain amplitude so that the electronics can extract the appropriate data and voice information from the signal. We have a signal generator generating a 1 kilohertz 2 volts peak to peak input signal, which goes into 47 microfarad capacitor. That capacitor there is simply to block any DC signal that we've set up on the circuit from feeding back to the signal generator. We have a 15 volts DC supply, electronic kits, modular kit, easy to wire components between pillars, very quick and very reliable. Not easy for components to fall out, as in breadboards. Digital oscilloscope and a digital meter on the right hand side. We have a 33k ohm resistor and a 4k 7 ohm resistor to set up the bias point on the base of the transistor, such that we switch on the diode between the base and the emitter of the transistor to approximately 0.7 volts. We're using a variable resistor here because we did not have a 4k 7 ohm resistor in the box, so we're using a variable resistor. We have a 5k 6 resistor connected on the collector, 1k ohm resistor connected from emitter to 0 volts. Purpose of this circuit is to have amplification of the signal. So after AC amplification, we want to increase the current, the AC current and the AC voltage through the circuit, so we get power gain, for example in an audio amplifier to power a loudspeaker. We don't get more cumulative power out than we put in. We're using DC power to bias the transistor in the appropriate way so it acts as an amplifier. The gain is set in 2 ways. These 2 resistor values, the ratio of them, 5k6 divided by 1k, gives us a ratio of 5.6. That is an approximation of the gain of the circuit. We can see on the oscilloscope screen that the output signal is inverted with respect to the input signal. So we have a 180-degree phase shift. Each transistor that's manufactured has a slightly different forward current gain. So the 2 resistors here effectively override that, and we set the gain to an approximation of 5.6. If we look on the oscilloscope screen, we have an output of 10.4 volts peak to peak. We have an input signal of 2.0 volts peak to peak. So our gain is 5.1. That gain is slightly lower than the approximation of these resistors because the full equation to work out the gain accurately is more complicated. But as an approximation, we use these 2 resistor values, and we have a bigger signal coming out, 5.6 times bigger than the signal going in. The digital meter on the right hand side is showing 7.99 volts. In order to bias the transistor correctly, we want a DC operating point of the transistor on the collector to be approximately halfway through the power supply voltage of 15 volts, ideally 7.5. We can operate the transistor also as a digital switch by making small adjustments to the circuit. If we replace the 1K resistor with 100 ohms, we no longer have the transistor working in its linear mode. So what we mean by linear mode is we have microamps going into the base and we have milliamps coming out of the collector emitter junction. We have current amplification. If we change the base current, we have an appropriate change in the collector current. Now, with the 100 ohms instead of the 1K on the emitter, we are operating the transistor either in saturation mode when it's fully on or fully switched off. And what we get out now is effectively a square wave output, a 1 and a 0, a digital signal, a binary signal. It's no longer a sine wave, even though we've got a sine wave input. If we want to mimic TTL levels of 0 to 5 volts, we can break the circuit here and tie the collector to 5 volts rather than 15 volts. If we adjust the volts per division on the digital oscilloscope, we can see that the signal is operating between, let's get there, down again. The signal is operating between 0 and 5 volts. We're on 1 volt per division, 1, 2, 3, 4, 5. So we are mimicking our TTL logic levels, voltage levels. If we input a square wave into the system, if we look on the oscilloscope screen, again what we have is inversion. We have a signal coming out that's 180 degrees out of phase. It's an inverted signal. So what we're demonstrating is the action of a digital inverter or NOT gate. And in this small modified circuit from the amplifier, by changing emitter resistor and the collector voltage to 5 volts, we're now operating the transistor in its saturation mode rather than an amplifier.